All right, welcome to this explainer. Today we're diving straight into the graphical method for solving linear equations in two variables. If you've ever stared at a set of algebraic equations and wondered what they actually look like mapped out in the real world, you are in the exact right place. Let's make this visual.
Here's our roadmap for today. We'll start by explaining the graphical method itself, then decode our first equation, plot the second one right alongside it, and finally track down that all-important intersecting point. Let's get into it.
Section 1. The graphical method explained. Visualizing simultaneous equations.
Take a look at this. This perfectly illustrates our end goal. We've got two distinct, brightly colored lines cutting across the grid, one representing the equation x plus y equals 5, and the other representing x minus y equals 3. See how those geometric paths cross right at the coordinate 4, 1? Well, that specific spot is definitely no accident. That's our shared solution.
So, why does this matter? Well, the intersection point is simply the exact xy coordinate where our two graphed lines cross. You already know that every single point on a line is a valid solution for that specific equation. But that one glowing spot where they intersect, that's the hidden treasure both equations share. It's literally the only set of numbers that makes both statements mathematically true at the exact same time.
Moving on to Section 2. Decoding the first equation, transforming algebra into geometry.
Let's tackle our main practice problem and decode our first equation right here, x plus y equals 0. To solve this graphically, our very first microstep is to generate a reliable set of coordinates because, we can't just draw a neon line out of thin air. We need an exact step-by-step blueprint to show us where this equation lives on our Cartesian plane.
And we do this by setting up a super simple table. By picking some easy arbitrary values for x, say 1, 3, and 5, we can quickly calculate the corresponding y values. Since x plus y absolutely must equal 0, if x is 1, y has to be -1, right? If x is 3, y drops to -3. And if we plug in 5 for x, y balances the whole thing out at -5. So pulling those pairs straight from our table, we've now got 3 precise dots ready to be plotted on our graph: 1, -1, 3, -3, and 5, -5. Connecting these dots is going to give us a perfect straight line representing that first equation.
All right, Section 3, plotting the second equation, generating the second line.
Next up, we tackle the second equation in our system. 2x minus y equals 9. Just like before, we need to create another table to turn this string of algebra into actionable geometry. We're looking for the specific points that satisfy this slightly more complex relationship. Let's see how this builds out. When we input an x value of 2 into the equation, well, 2 times 2 is 4, 4 minus a -5 gives us our 9. Testing an x of 3, we discover the corresponding y is -3. And when we try an x value of 4, the math dictates that y must be -1. See how that flows? Extracting those values gives us our second set of coordinates to plot on the exact same grid: 2, -5, 3, -3, and 4, -1. Boom! We now have the architectural plans to light up both of our lines.
Let's briefly pause here and review the exact methodology we just used, just to make sure we've got a rock-solid foundation for any problem you might face. Step 1, create a table. Step 2, select simple values for x and calculate the corresponding y. Step 3, bundle those into coordinates to plot on the graph. It's a clean, totally repeatable system.
Which brings us to Section 4, finding the intersecting point, discovering the shared solution. Now for the absolute best part, bringing both sets of points together. Before I reveal the final answer, I want you to look really closely at the data we've just generated. Can you spot the visual puzzle yourself? Remember, we know the intersection point is the one coordinate that exists on both lines. When we place these two sets of data side by side, it's pretty wild. The exact matching coordinate jumps right out at us. On the top, we've got our points for equation 1. On the bottom, equation 2. Scanning down those lists, yep, there is exactly one pair that is perfectly identical. And there it is. The shared solution is the coordinate pair 3, -3. This means our lines cross exactly when x equals 3 and y equals -3. If you draw these paths out on a physical graph, this is exactly where they collide. Game over, we found it. Let's do a quick wrap-up of our visual proof here. We successfully took abstract mathematical equations and transformed them in organized tables. we calculated specific coordinate pairs. By comparing those pairs, we easily identified the shared intersection point. And through that entire process, we solved the simultaneous equations graphically, totally bypassing complex algebra in favor of pure, beautiful visual logic.
So, the next time you're facing down a set of simultaneous linear equations, will you use this structured graphical method to clearly plot your path to the solution? Just remember that every equation is really just a hidden geometric line waiting to be drawn. It makes solving them so much more intuitive, don't you think? Thanks for joining me for this explanation.